Good morning. Well, good afternoon, actually. Thank you for coming. Thank you for showing up. I hope you're not here just to have a nap, because we are going to talk about Loom in a JDK 25, and with a serious focus on two elements. First, what has been done in virtual threads since 21, and I'm thinking about one topic in particular, which is the fact that the issue on synchronization has been fixed. This is what we want to talk about. And then we'll focus on two other things, scope values and structured concurrency. Knowing that scope values is a final feature in the JDK 25, and structured concurrency is still in a preview feature, and will also be a preview feature in 26.
Yeah, basically the API was redone. So.
Yeah. The name of the class is the same. Technically speaking, it's not the same because it's an interface now, but yeah, that's okay. So my name is Jose. If you want to know more about many things, not everything, just many things, you can follow this QR code. Will take you to a GitHub page with links with all the junk I publish on the internet. I work for Oracle as a Java developer advocate. And Remi, you don't work for Oracle, sorry. The logo is still there. It should not be there because it doesn't.
So yes, I'm a professor at a university really near Paris, basically in between Paris and Disneyland Paris.
Is it still Disneyland Paris?
I don't know.
Changed name several times. Never mind. And you don't have any link, but just Google for your name.
Yes.
And, plenty of content everywhere. Just a little ad, because, yeah, let's do that. We have the dev.java website that we manage with the Java Developer Advocate at Oracle. That is announcing Java 1 2026. So even if you can't make it to San Francisco, if you're there, it's probably because you're interested in the new things that are currently being published in the Java space. And usually during this event, there are plenty of announcements and things that are recorded and they can watch later on YouTube. So you should definitely follow that. If you can come, it's really great. Great people, great, yeah, everything. Yeah. Great vibe, great mood. Please do come. You can also tune in on the Java YouTube channel, plenty of video content. And if you're interested in 25, you have this series called Road to 25 that will take you hopefully from 21 to 25. and that's it. Who is using the JDK 25 among you? Maybe quick show of hands. Oh, that's, yeah, a nice 15%, I would say. Yeah. Something like that. 21? Oh. That's the large majority of you. Congratulations. 17? Oh, that's quite a few hands, but not more than a few percent, I would say. 11? No one? Oh, 1%. Two hands. 8? Oh, come on.
Oh, we are sorry for you.
Yeah, we feel for you. Older than 8? Like 15 years ago version of Java? No one. Okay. Great. So yeah, 25 is here. It has been released just a few weeks ago, and there are plenty of things. If you want to connect, if you want to give feedback, if you want to follow everything that is happening, you need to connect to the mailing list from the OpenJDK website. This is where everything is happening, and happening in the open. I mean, if you really want to know what is happening in the Loom space, just connect to the Loom mailing list, and all the links are there. And if you want to be really on the edge of things, and you want to download 26, because 25 is so September, well, you can. There are already early access versions of 26. And if you're interested in Valhalla, you have early access versions of Valhalla too.
And soon, in 2 or 3 weeks, we should have a new preview.
Ah, Valhalla, that's awesome. I think you have a talk on Valhalla later this week.
Yes, okay. Tomorrow at 12 something.
Yeah, so maybe you can check the official agenda.
Yeah, it's better.
But you definitely want to first see this talk if you're interested in Valhalla. Okay, so now we're going to talk about the project Loom. I love this image of Duke weaving stuff with this Loom, by the way. The first preview was in the JDK 19. That was in 2022. Can you believe it? 3 years ago already. And you have here a tweet by my friend David, who tweeted about the pull request of the Loom project, just to give you an idea of the engineering effort behind the Loom project. It's really huge. I mean, 100,000 lines of code have been changed in a code base of the JDK. So it was really a big effort. They were made final in 21, but still with an issue. The fact that you have this pinning issue, and we're going to talk more about it in a minute. And as we said, it was sold in 24, so that's one reason why actually, one of the big reason why you should move from 21 to 25 if you're using virtual threads. This is this fix that you now have in 25. Scope values, also part of the Loom project, were final in 25. So that's the JEP 506. And I can only encourage you to try to read the JEPs because they have been written with the idea that people are going to read them, actually, which is not the case for everything that you write. For instance, specification. Who likes to read specification? Yes, no one? Okay. Structured concurrency, that's the 5th preview since 21, and we're going to talk a lot about it. And it will still be a preview in 26. We already know that, and we already have elements that are going to be added, and we're going to talk briefly about them. About the adoption, I don't know of any major project around that did not announce some kind of support for virtual threads. So I just put some random images there. There are probably many missing. Let's say that Elidon, for instance, starting with the version 4, I think, is entirely built on top of virtual threads. So don't need to
it was fully rebuilt.
Yeah, fully rewritten to support that. What is Loom about? Loom is about fixing concurrency issues. And the first question you should be asking yourself is, why do I need concurrency? And if you don't have any answer to this question, maybe you should stay away from concurrency, because concurrency is a hard topic to master, to say the least. And it brings many bugs that are just impossible to fix, like race conditions. Everybody loves that. So if you don't know why you need to use that, don't use it. Okay. If you want to summarize things in just one sentence, it is needed to achieve low latency by doing several things in parallel on the same CPU. And by the way, by now, the paradigm that you're probably all using, or all be using for even like 10, 15 years, is the callback-based reactive programming. So Loom is actually bringing solutions to solve the same kind of problem as the problem that callback-based reactive programming wants to solve. So let us talk about that, and let's talk about virtual threads. And we're going to take a small examples. First, I have some service that is making queries on the network, maybe the internet or something else. I don't care about, by the way. And first, you are going to read images, and then to read links. And you want to build a page with the images and the links. And we all know that this code is buggy, to say the least, and very inefficient, obviously. So starting in 2004, Java 5, we have this new Java util concurrent package that is being added to the JDK. And that brings a new pattern of code based on the use of the executor service object. And basically, an executor service is a pool of threads with some method to submit tasks in a form of runnables and callables, and you get a future in exchange that you can analyze to get all this. And you end up writing this kind of code. And there are many things that are wrong with this code. Some are obvious, some are less obvious. How many bugs do we have here? I think 4.
Yes, something like this. 3 or 4. Like it depends how you count.
Yeah. The first kind of bug is that you block threads. And blocking threads is bad, right? Why is it bad? Well, when you ask this question around, actually, you realize that there are many more people that will say blocking the thread is bad than people that can explain why blocking the thread is bad. This is about repeating, okay? Artificial intelligence is very good at repeating, but yeah, not much added value in that. So it blocks threads. How many threads does it block? Well, probably 3. It actually depends on the executor service you have. Okay, it blocks the first worker thread from the executor service, and there's the second one with read links. Now, if you have only one worker thread in executor service, you're going to block only one, because there's only one. But the main thread is also blocked because you're calling get, and get is a blocking call. So that's 3 threads. Blocking a platform thread is bad because you are actually blocking a very expensive resource for an amount of time that is in the order of 100 milliseconds. In a nutshell, that's the main issue. Second one, and that's probably the most annoying bug here, is that it can lead to a loose thread. That is a thread that is doing something that you don't know about, and that you can't know about, can't analyze, and that will just mess up with your application and not add any value to your application anymore. And it's because of that. If f1.get crashes, you have a timeout here. So you may have this exception if the reading of the images is too long, right? It crashes, so it breaks the main thread, and so that f2.get is not called anymore. So because f2.get is not called anymore, even after 1 second in this case, because this is the timeout you chose, okay, this thread will continue doing its job. And if the job is just buggy, like blocking forever, doing nothing, then you just lost a thread, and you can't reclaim it, you can't send anything in this thread anymore. Okay, yeah. But this thread could also be lost. Yeah, sorry.
Yeah, and the main issue is that usually you reuse your executor service, so you may have lost a thread forever. You may have lost this resource forever, or at least for the duration of the running of your web server.
And this is annoying. So this thread could be lost because it's just blocked and it doesn't do anything. And in that case, it will just consume memory, but it will not consume CPU anymore. But it could also be lost in some kind of infinite loop and actually consume some CPU resource. So you're really in trouble if you do that. And the third one is just it's hard to debug. And why is it hard to debug? Because the stack traces you have when you have exceptions in such code doesn't give you any information about what is happening actually in your application. And we're going to see actually stack traces to show you that precisely. So there are 3 issues to be fixed in concurrency. First, blocking a platform thread is bad. It needs to be fixed. Blocking a thread should be okay, and we're going to see that. Second, you want to have relevant stack traces when exception is thrown somewhere. This stack trace should take you to the place of the code, of your code, where the exception was thrown and where the problem was actually noticed. And we are going to see that virtual thread give you that. And third, having loose threads is a waste of resources, and you don't want that anymore. This is also an issue that needs to be fixed. Okay, so that's quite a program. And well, let's go. So first, a thread is a wrapper on a platform or kernel thread that takes about 1 millisecond to start and consumes 2 megabytes to store its stack upfront. Why is it allocated like that? Because this piece of memory needs to be contiguous, and so people tend to allocate not too much but not too few memory so that they can store everything they need.
Yeah, technically it depends on your OS.
Yeah.
In Linux, it tends to reserve less and do. When you will ask for more stack, it will provide you the value because it plays with virtual memory. But if you are on macOS, by example, you have the whole memory which is reserved upfront.
And the context switching, we probably heard about of that, takes about 100 microseconds, which is also actually a lot of time considering the speed of current CPUs. So it means that you can only have several thousands of them. The number of platform threads that you can have on a regular machine is in the order of several thousand due to all these limitations. And by the way, we did this demo a few years ago, and there was a hard limit on your Mac at the time, which was 4,000 platform threads.
Basically, it's the hard limit is the memory you have, and memory is not that cheap on Apple.
So it means that if you want to write your code that is doing some network calls with this old pattern from the early 2000s, late 90s, where you have one thread that is handling one network request, and that leads to very easy to read code, by the way, it means that your application is limited to the number of threads you can have, which is in the order of the thousands. So let's take 4,000. It could be a little more or a little less. Doesn't matter. So if you consider that the CPU time that the managing of a request is in the order of the microsecond, which is probably the case, then it means that your CPU, on the one hand, your CPU should be able to manage several million requests per second. But due to this model, this programming model that you're using, one network request per thread, the limiting factor is actually the number of threads you can have, which is only a few thousand. So you're missing a factor 1,000 there between what your CPU can do and what your OS can give you as thread resources. And this gap needs to be fixed because a factor of 1,000 is actually a lot.
Yeah.
It's a lot. So it means that the model, one request per thread, does not work with platform threads. Okay? This is the conclusion. And this led to a first solution, which is the reactive programming solution. Instead of having one request per thread, you need to be able to manage many, many requests per thread. Okay? And how many requests per thread do you need? At least, it's in the order of the 1,000, because it's this factor 1,000 that you have between what your CPU can do and the number of threads you can have. And if you can manage all your reactive system in one thread, it means that you should be able to manage to send 1 million requests in this only thread. So it's between 1,000 and 1 million. So this pattern of code, which was nice to read but not usable because buggy, actually becomes this kind of code, which is written with the Completable Future API. Do you like it, Remi?
Oh yeah, I love it. Because you have forget.
What did I forget?
How to deal with errors.
Yes, there's no. Well, technically speaking, there's this one complete stuff. Yeah. But yeah,
do something in the gray.
Do something. Do something. So obviously, here you have something that you can read and they can understand easily, and here you have some kind of ugly pattern of code that you need to work with, because this is actually the current solution that everybody's using. Maybe not with the Completable Future API, but callback-based reactive programming leads to this kind of code. And it's wrong on many points, actually. The readability being one of them, but certainly not the only one. How is your platform thread being used when you're using the Completable Future API? Okay? Suppose that you have one platform thread that is doing everything. You have a first piece of task that is coming in your supply async method. That's a lambda. Okay. All your network request and a response cycle is actually split into small lambdas that are just doing one thing one at a time, and that should never block. So the first lambda is coming, and after a while, the lambda is done because it launches the network request. And after a while, the response will arrive. So you have a signal that triggers something in your callback, in your asynchronous framework. Could be the Completable Future API. Tell, hey, the data is there. So now I can call the lambda that is going to consume this data and do something with it. So after a while, you have a second lambda that is triggered by your framework. And after some more while, maybe you're doing something with this data to launch another network request. And after another while, you will have another piece of your process that is going to be executed. So your process is actually split into small lambdas that are going to be executed, and all the wiring of these executions is managed by your framework, which is amazing, to be honest. But because this platform thread is available, of course it can manage another request, maybe it's the same request or maybe it's another one, that will block and stop being executed by this platform thread. And then when the data is there, later on, the rest of your request response cycle will be invoked by your framework. And the same, maybe there's another piece of data that will arrive and that will trigger some other execution. And of course, you can have another request from totally another part of your application that is going to be executed, that will wait for its data. Its data is going to arrive from somewhere, the network probably, and then yet another one, and another one, and another one, until the platform thread is actually busy 100% of the time. So when you're using this kind of approach, actually your platform thread is busy 100% of the time. So there's no way for you to get better performance because your platform thread is already busy. And it cannot do anything more than what it is already doing. Okay? There is one point that you absolutely need to keep in mind is that you should never write some blocking code in these small lambda expressions. Because if you do, this code will block for an amount of time which is in the order of the millisecond, 100 of milliseconds, and the time scale of this diagram is actually probably the 100 of the microsecond. All right? So you will block your platform thread, and you will prevent about 1,000 of these small lambdas to be executed during this time. And it will be, of course, very bad for your application. Now, how could you fix such bugs? Because it's a bug. Well, the only way you can fix this bug is actually to analyze your code and check if your lambdas are blocking or not. So this is code review, basically. Good luck.
You have some framework in Scala. You have ZIO, by example, that help you to write code that way.
What about debug? We talked about the stack tracers. So what is happening if in this method readImage, you have an exception that is thrown, and let's suppose that it is line 27. Well, if you're just calling this method from a main class, all right, you have a simple stack trace, which is just this one, and that will take you exactly within the readImage method on line 12, and you know that it was called from the line 27 of your main method. And this is really great because you know exactly the context and everything. You have basically all the information you need to debug your application. And it's not only about debugging, it's also about putting a breakpoint and being sure that what the thread that is blocked on this breakpoint is the thread you want to debug, is the process you want to debug. What does the stack trace look like if you submit this to an executor service? So that's the first pattern we showed you just a few minutes ago. Okay, and you you create this page just like that. Well, it becomes a little more obscure, I would say, because what you have is actually the stack trace of the thread that is currently executing your lambda. And the thread was created when your executor service was created. Usually in a Spring Boot application or this kind of application, your executor services are created when you launch your application. Okay, so this thread takes you to the launching of your application. It does not take you where you submitted your lambda to this executor service, and certainly not where you created this lambda. Actually, if you check, it takes you to the get method, which is on line 32, and after that, you're in your executor service. So you know where the get method crashed, but you don't know where your lambda was submitted. If it's close enough, that's probably okay, but it could be miles away in your application. And what is going to happen? So now I have some code to manage the error because I need to have the stack trace. All right, so that's the completable future API. At least on the previous slide, here I have a call to get that is explicit. Okay, it's me that is calling get in my main thread, and it takes me there. But here, I don't call get. Okay, my framework is probably calling it in some kind of internal layer, and it brings me the result, and that's it. So the stack trace I have is this one. And with such a stack trace, good luck debugging. You don't have any information.
Your application is doing something?
Yeah, oh yes, absolutely. It's running my framework most of the time, obviously. And it's the same problem if you want to profile your application. Because actually what you're profiling is not your application, it's your framework. So it has an impact on debugging and profiling.
Yeah. basically profiling is based on having stack trace that works correctly. You need snippet of the stack trace.
So async programming is efficient. There's no doubt about that. It keeps your platform thread busy, and this is exactly what you want. So you get the best performance you can out of your CPU, as long as your framework is not creating too much overhead. But this is what frameworks are doing. The programming model is hard to read, to write, and to test. So it means that if you want to change something, well, you probably need to rewrite what you were writing. It's impossible to debug because the stack traces that you get don't give you any information on what was going on. And it's the same if you put a breakpoint in a lambda in a computable future. How can you be sure that this is the process that you want to debug that will trigger this breakpoint? I won't say it's not doable, but it's very hard to do. You can't profile it. And writing non-blocking lambdas is on your shoulders as a developer. Okay? So that's kind of a responsibility, because if you fail writing non-blocking lambdas, then you are going to slow down all your application, not only the process you're writing.
And one problem you have usually is that you are using a dependency. You are using a dependency and everything works, and then you upgrade the dependency, and now there is a blocking call in your dependency code. And it doesn't work anymore because you have just done an upgrade on your dependency.
This is why you should not upgrade. Is that the conclusion of what you're saying? Come on.
What I'm saying is when you are in this scenario, it's really hard because technically you have not changed your code. But now you have an issue.
But fortunately, there is a second solution. So the first solution was to say, okay, platform threads are heavyweight. They eat up a lot of resources. So we need to send them a minimum of 1,000 requests, 1,000 lambdas per platform threads. But there are actually a second solution, which is to build another model for thread, which is much lighter than the current model of platform threads. And how much lighter? Well, it has to be this factor of 1,000, which comes from the difference between the network latency and the time scale on which the CPU is working. This factor 1,000 has to be there, right? So this virtual thread needs to be 1,000 times lighter, memory-wise and CPU-wise and everything, than your platform thread. So on a machine where you can launch 1,000 platform threads, you need to be able to launch 1,000,000 virtual threads in the same configuration. Okay? Yeah. Many people will say, oh, launching 1,000,000 virtual threads, that is just marketing. Yeah, I'm not going to say it, but you see what I mean. Okay? Actually, it's not. It's not. This is what you need. If you gain just a factor 500, it will not free you from having to write reactive programming. You need to have at least a gain of 1,000. And it also needs to provide a simpler programming model. Okay, that is the callback-based approach. You don't want that anymore. You want to be able to come back to one thread, one request model, because it's much simpler. And actually, if you can achieve that, you'll be able to come back to fall back to this model naturally. And it needs to make debugging possible, that is to have meaningful stack traces, and profiling possible for the same reason.
So how it works? We have tried to do some drawing to explain how it works, and it will also explain why we had trouble with the synchronized block. Wait. So basically, the way it works, you have your platform thread, and you have some virtual thread. And the idea is, basically, if you are blocking a virtual thread, instead of blocking the platform thread, you will do something else. So when you start a virtual thread, you start it on top of a platform thread, what we call a carrier thread. if there is a blocking call, basically the whole stack of the virtual thread will be copied to the heap, which is nice because now my worker 1 is free to take another virtual thread and run it on top of the worker thread 1. After some times, the OS will say the data are available, you don't need to block anymore, and you can copy back the stack on one of the worker thread. So it can be on the same thread. You want it to be on the same thread because you already have the cache that are hot and so on. So if it can be on the same thread, this is great. But if that thread is already, this platform thread is already used by a virtual thread, it can come back in another virtual thread. So technically, this is not exactly how it works because the implementation tried to avoid to do a lot of copy. So you have quite extensive trick to avoid to do a lot of copy and try to do some lazy copy of things. But conceptually, this is the model of how it works. There are some issues that will avoid you to copy that thread. The problem is if the virtual thread contains a C stack. So you can have this kind of things when your Java call a C code that will call another Java call. In that case, right in the middle of the stack, you have a part which is managed by C. And in C, you have an issue because you can use the address of the stack. You can stack allocate an object and send its address to somewhere, store it somewhere. So in that case, if you have a C code right in the middle, you cannot copy the thread because you cannot copy the stack because when it will come back, it may not come back on the same worker thread, so not at the same address, which means that if all your code is 100% written in Java, you have no issue. But if right in the middle of your stack frame you are using C code, then you're dead. You will block. The virtual thread cannot be, the stack of the virtual thread cannot be copied. So basically, the worker thread is blocked. It's what is called pinning. Because basically, the virtual thread cannot be copied to the heap. That's why, I don't know if you know, but the world reflection was rewritten for Loom. Because before Java 19, basically the way to do reflection was to calling C code that was calling Java code when you do something like method.invoke. And it has to be changed because if you want to use a virtual thread, the whole code has to be written in Java. So currently we have still some code that are using C code even in Java. By example, if you run a static block, I don't know if you know, but you have a lock which is taken by the VM, so you cannot have several threads that run the same static block. This is done in C code. This may pin your virtual thread. You may use some libraries like Netty. Netty provides some really, really nice native implementation. But in that case, the C code will call your Java code. So right in the middle of your stack, you will have a C code. So virtual thread will not work. If you use a new FFM API, you can call a C code that will call a callback return in Java. You have exactly the same issue. So basically, if you are only using Java, that's nice. If right off the middle of your stack, you have a C code, you have a C stack, then you are pinning the virtual thread to the current carrier thread. This is exactly the issue we have with synchronized block that was fixed in Java 24. So I will explain exactly what is the issue. So synchronized are quite used heavily in Java. Usually if you have a problem of concurrency, the usual idiom, at least if you take a look to the code generated by LLMs, is to put some synchronized everywhere and magically at some point it will work. So synchronized are heavily optimized in Java because of that, which means that we have a kind of a double-step process, which is if only one thread tries to grab a lock, instead of allocating the data structure to store the lock, the light data structure will be used on stack to avoid doing allocation and things like this. And then only if there is another thread that tries to grab the same lock, then a proper data structure will be allocated to manage the fact that you need to have a wait list of threads that are waiting on that lock. And at some point, that lock, if not used anymore, it will be deallocated. Historically, it was done during a save point, but now this is done asynchronously with the application. So just let's take an example. I have a main that called build page. So you can see on that part that the main calls the build page. What you see is what we call stack frame. A stack frame is where you put your local variable when you do your computation. Technically, this is not how it works in Java. It depends, because in Java, you can be in the interpreter or running assembly code that was cheated. If you run assembly code, all your local variable will be in register, and so you have mostly nothing on the stack. But if you are in the interpreter, you will have everything on the stack. And if you call methods that have a synchronize, what is done before Java 24 is that basically when you synchronize on an object, so this is before calling synchronize, if you take a look to the header of an object, if the object is not taken by any synchronize, you have 2 bits that we call the log bits that are 0 and 1 by default. And if you enter a synchronized block, then instead of having 0 and 1, you have a full pointer. And because the pointer is aligned on a 32-bit address, then you know that the 2 bits on the right are 0, 0, which means that you know that one thread has taken the lock. In that case, the header of your object is referencing somewhere at the beginning of the stack frame of your method. It's quite easy for the VM to see if there is a synchronize in the bytecode and to reserve space for it, which means that if you have only one thread that enter a synchronized block and go back and exit the synchronized block, there is no allocation in that case. So this is fast. and it works really great. The main issue is that now, from the virtual thread point of view, we are in trouble. Because now we have an object from the heap that point directly to the stack. So the stack cannot be copied anymore. Because when we will come back, we will not come back at the same addresses. So it will not work anymore. So that's why when you do an IO call inside the synchronized block before Java 24, you are just out of luck. Because the stack frame, all the stack frames, all the stack of the virtual thread cannot be copied into the heap, because there is a pointer to one part of that stack, which is kind of a sad thing.
Unfortunate.
Yes, I mean, it's a really great optimization. It works for a long time. I was not able to track exactly when this optimization was added because it was before that Java was open source. So basically, the way synchronized work has to be changed. And there is something which is, in terms of engineering, all the I enter a synchronize and I exit a synchronize are returned in assembly code to be fast. So all the code on all the platform has to be changed to have a new way to manage the synchronized block. One thing that saves us is that at the same time we had the Loom project, another project called Lilliput was running. And the goal of Lilliput is to reduce the size of the header. And in order to reduce the size of the header, they had to change the locking algorithm too, which is great. So this is the way it works for Lilliput. If you are before entering a synchronized block, the lock bit is 0 by default. And we have a new structure, if you can see, at the base of the lock. We have something called the lock stack, which is, I think it's 8 by default, 8 values that are free to store pointer in them. And when you want to allocate a lock, basically you can use the space inside the lock stack. So instead of having the data structure be at the beginning of a stack frame, the data structure is shared and is at the beginning of the stack. And instead of having the header of the object pointing back to the data structure, it works in the other way, which is inside the log stack, you have a pointer that references directly your object. So if you want to know if the object is lock, it's quite easy because the lock bit has been changed. And if you want to know all the lock inside your stack, it's quite easy too, because you can take a look to the lock stack directly. So by doing this, now there is no pointer in the middle of the stack anymore, which means that for a virtual thread, it can be copied with any problem. There are more problems for the GC because now the lock stack can point directly to an object. So if the object is moved by the GC, you have to rewrite the lock stack zone, but it's another route for the GC, so it's not really an issue anymore. Which means that basically with that ID that was introduced in Java 24, now you don't have to care about your synchronize or exactly blocking inside a synchronize, because the code of the whole VM was changed to use this new locking mechanism, I think.
So now that this issue is fixed,
yeah,
it was not really an issue because if you don't block in your synchronized block,
yeah, there is no issue if you don't block in synchronized block.
The issue was there only if you run blocking code, and by blocking for several hundred milliseconds inside the synchronized block. So now we have this virtual thread object, which is an instance of the virtual thread class, and which is a regular Java object. Okay, it's just like any Java object. So it's just like creating an array list. An array list is you can have as many array lists as you want. You can have as many virtual threads as you want. And blocking a virtual thread does not block its carrier thread anymore, even with the synchronized block, which is the issue that was fixed. And actually, virtual thread should only be used for blocking calls. If you want to run, for instance, a parallel stream, running a parallel stream, trying to run parallel streams in virtual threads will not give you any better performance because a virtual thread is an overhead compared to a platform thread. So if you do not have this gain of running a blocking code that will not block the underlying platform thread, you're just paying the overhead without any benefit. So it will actually slow your code if you try to run your parallel streams in your on top of virtual threads.
Yeah, any computation. There is no point to run a computation
any in-memory computation. There is no point in running them in virtual thread because you're not doing any side effect or blocking calls in parallel streams, right? You don't do that. No.
They don't use parallel stream.
Don't use virtual threads for long-running in-memory computations.
Please.
Okay? Don't do that. Don't do that. If you check how your platform thread is used when you run a virtual thread, set of virtual threads on it. So remember that you have this pool, which is the common function pool, by the way. The common function pool of workers, and you have a virtual thread running on top of them. So if you have a first task that is coming, that is being executed on one of these workers, let's just take a look at one of these worker thread.
So this technically, it's the same pool, but it's not the common fork join pool. It's a fork join pool, but not the common fork join pool. And it's configured slightly differently. If you're using the common fork join pool, you want to aggregate basically, when you use a fork join, you fork all the thread and you gather from the bottom to the top.
Yeah.
But when you run a virtual thread, you want to run the first you have created. You
want to keep the order instead of inverting.
Yes, exactly. Yeah, exactly. So basically, it's a fork join pool, but configured differently.
So if you send a virtual thread to this fork join pool, the worker thread will see a virtual thread that is coming with some long code that is to be executed in it. And then there is a blocking code in it. So when the code blocks on the network call, this virtual thread will be removed from the stack of the platform thread and copied to the heap memory, as you saw it. So it's just like the virtual thread is gone and will come back later. When the data is available, this virtual thread will come back and be executed, hopefully on the same worker thread, maybe on the other one, but should be optimized. And then it could happen again. another blocking call, another piece of data that is waiting, that is coming later from the network, and then your virtual thread will be done. Okay? But in the meantime, of course, another virtual thread could show up that is blocked, the data is coming, and then another blocking call, and the data is coming again. And then the third one that is blocked, come back later, and come back later again with more data, and then another one, and then another one, and then another one. Okay? So from the platform thread point of view, because a worker thread is a platform thread, what is the difference between running virtual threads and running a completable future API that is doing the same thing? Well, if you see any difference, it means that the copy-paste from PowerPoint is not working, because this is basically what I did. Okay, so there's no difference between both. This is the point. So if you have in mind, oh, we're going to use virtual thread because we are going to gain 100% performance just by using that because we read that on a blog post or on a stupid YouTube video, then no, you're not going to get any better performance. Virtual threads are not about getting better performance. They are about writing better code that is more readable and about getting meaningful stack traces when you have exceptions in your code. It's not about getting better performance because your CPU is already busy 100% of the time. So you cannot squeeze any more, performance from your CPU. There is one big difference, though, is that in the second case, where you have virtual threads, the responsibility of removing the lambda from the platform thread is gone from your responsibility. In virtual threads, you write blocking code. In your completable future or reactive framework API, if you write blocking code, it's a bug and you need to fix it. So that's one less responsibility on your shoulders. And I must say that I'm quite happy I don't have to take care about that anymore. Okay, just write simple plain blocking code and that's okay. This is actually what you should be doing. So the most basic code you can write is this one. It's blocking, but as long as you run it in a virtual thread, it's okay. This is what you should do. And if something goes wrong, so here I have this callable, and I'm submitting this callable to a special executor service that you have, that was added also in 21, called new virtual thread per task executor, which just doesn't pull anything because you don't need to pull virtual thread. You just create them when you need them. Okay, you submit your callable, you execute it in a virtual thread, and then you get your future, and you get your future, and you're blocking again, but since you're in a virtual thread, it doesn't matter. And if you have this stack trace in this one, well, the stack trace will take you exactly where you want to be taken. Okay? You know where it was in some service, line 12, and you know that this callable was created on line 78, which is exactly what you need, and you know that it was submitted on line 81. Well, the get call was on line 81. Okay? So you actually have all the information you need to properly debug your code and to see, to fix it if this is what you need. Usually when you have a bug, you want to fix it. Usually. All right, so that was for virtual thread. Scope values. You want to talk about scope values?
Yeah, why not?
You have plenty of things to say about ThreadLocal variables.
So now we have a problem. Now that we have 1 million virtual thread, we have a problem with ThreadLocal. So basically, the way ThreadLocal works, you can see it as this is a hash map that associates to one thread, one value. But now that we have 1 million virtual thread,
the hash map becomes bigger.
Yes, quite bigger, and basically to the point where the hash map mechanism takes times out of your application. So, what's wrong with ThreadLocal?
Can we just ask these people here, because we have an audience, you know?
Oh, yeah.
Who is using ThreadLocal variables?
No, it.
Oh, that's okay.
Who don't know that your framework is using ThreadLocal.
So it means that all the others actually, are in this situation. Who is not using Spring Boot? Quite a lot of people. Okay.
Yeah, but they are all using Quarkus.
Not all of them.
Actually, using ThreadLocal is quite nice. So basically, all the idea of ThreadLocal is to say, I don't have to send a parameter everywhere if I want to know my current user or something like this. I could put it in ThreadLocal and get it when I need it, which is quite nice. The ID is nice. The API is not, which is basically you can mutate the value of ThreadLocal everywhere you want, which means that by definition, the VM will not optimize anything. There is no possible optimization when you can mutate everywhere. The other problem is that the way to use it in terms of pattern, you may use it wrong, which is basically it's the memory is allocated. The memory where you put the value is allocated lazily when you ask for it. But if you want to deallocate things, you have to call remove explicitly, which is not nice. We have a language with a GC, so no problem with deallocation. But for ThreadLocal, you have to call remove explicitly.
Wasn't remove method added as long in Java 5 when the executor service pattern was added?
I think it was added after. Or I think there is a point where we had ThreadLocal, but no remove. Yeah, I think ThreadLocal is from 1.1 or 1.2.
Yeah.
But the method remove was added something like
super
5 years after that. Oops, we have some memory leaks. We should do something about it. So the idea of scope value is to provide a better API to do exactly what scope value does. So not everything that scope value can do, but everything that basically what the people are using scope value in one way, and you would want just to optimize that way. So first, the value is not modifiable. The value you will store in a scope value are not mutable, which is nice. It means that we can have optimization. By optimization, it means you can have a cache, or better, you can inline the value inside the code, or things like this. They are not bound to a particular thread, which is really nice. And basically, you are defining it for one call graph. So for one method and all the methods that are called from that method. So how to create a scope value? So it's like creating a ThreadLocal. Basically, it's a factory method, but it works the same way. You will store it in a static final field. And then when you want to use it, you have two methods. The first one will define what is the value for the scope value. So here, the scope value key has the value key underscore 1. And this value will be available for the method do something smart and all the methods that are called from do something smart. That's the way it works. You can note that the API is using lambdas. So the API will deallocate or do whatever it has to be done to remove any value. So there is no way to get it wrong, basically. You don't need a remove method. on them to work. And
I don't think you can do that, actually.
I don't think you can.
So just skip it. This is a bug.
Oh, our slide doesn't compile.
No, it does. It's always compiled in the slide. It's a nice thing.
So this inside the method, do something smart. If you want to get the value from the scope value, you can ask if there is a value associated. This is the method isBound, and you can get the value by asking using get. Technically, if you call get and the key is not bound, you will get an exception. If you are using Java 26, scope value are faster. There was a little optimization that was done that has almost been included in Java 25, but missed the window. So scope value are not transmitted to thread because the scope value is associated to basically a stack and stack frames. So you cannot lose scope value. And we will see later that if you want to have a scope value which is inherited to another method called graph, you can do it using structured task scope.
And this was pretty fast on scope values there. It's a very simple API, super easy to use.
Yeah, and we will come back when we do a demo.
During the demo, we'll show you how it's working exactly. Okay, so I just would like to very quickly introduce structured concurrency before the break. And then we'll have a coffee break if you want. And I would like to start with something you don't like, Remi, which is the goto. Why don't you like goto, Remi?
No. I like goto.
I started with who started with basic and gotos all over the place.
Yeah,
there's so many people. Look at that, and we love that, didn't we? Yes, because there was no debug, so there was only 50 lines of code, so that was okay. But then at some point, there's a guy who said that, by the way, that the
goto is harmful.
Evil. Yeah, can't remember. We need to. I'm sure there is a ChatGPT running somewhere that will give you a wrong answer. The problem with goto is that it can take you anywhere in your code. So if you're looking at a line of code and you say, okay, I've got a bug here, and you want to know where I'm coming from, basically, if you have a language with gotos, you can't know that. You can't know where you're coming from because you can literally come from anywhere. Okay? Well, guess what? Running something in another thread is just like issuing a goto. You have a main thread and you're just running instructions. And then at some point, you want to launch a task in another thread using the executor service pattern. So on the side, you have a worker thread within this executor service that previously was executing other tasks. Okay. And that is seeing this task that is coming from the main thread. But actually it doesn't know that this task is coming from the main thread. And this is why you lose. This is what we lost. The stack trace, the proper stack trace. And at some point, this instruction will come to an end. The result will be made available from the main thread, but all the context is lost. And this sending of a runnable is in another thread. From a, I would say, formal point of view, it's just like gotoing to this other thread. There's no goto, but this is still what you're doing. And after that, you're doing more instruction, and maybe you're launching a task in another thread, and it will be executed yet in another worker thread, which is different from the first one, but actually you don't know it because you submitted that to an executor service. And this is really bad, you see? For instance, if you want to have a scope value there, this is why you don't want to have a scope value precisely, because it will, if you allow scope values to be transmitted to other thread, this scope value may escape the scope of the calling of the original runnable or callable that you had. All right? And you don't want to have loose scope values, so you don't allow this kind of thing. And this is why structured concurrency is actually fixing that. The goal of structured concurrency is to fix this ugly pattern. All right? Structured concurrency you are executing instructions, and at some point you want to launch several tasks in parallel, like you're querying a server, several servers, and you want to do that in parallel to gather all the results and to produce a global results. So you're going to create some asynchronous tasks in the form of runnables or callables, submit them to a special pool of thread that is actually a structured task scope. We're going to see the code in a minute. And once this is done, all these threads will be killed. Your result will be the aggregation of all the partial results computed in all your threads, and you will carry on with your instructions. And in this pattern of code, you see that all the threads that you created actually are killed when you produce the result, and we're going to see the code to do that. Okay, so you don't have any loose threads that are escaping your method call anymore. And this is what the Structured Task Scope API and the Structured Concurrency API is actually giving you, right? And so if you set the scope values before you launch your asynchronous task, because you know that all these threads are not going to escape the flow of your instruction and the flow of your method call if you're actually in a method, then you're okay with transmitting the scope values to these virtual threads. So if your method, the method that we saw earlier, is actually creating a structured task scope, then the virtual thread created within the structured task scope will see the binding of the scope value that you have with the value that you set. Okay, and this is the reason why. Okay, and I need to remember that I need to click on this one. Right. So how is structured concurrency working? Structured concurrency is about creating an object, and you can see this object as a pool of thread. You create it when you need it because it's based on virtual thread, and creating virtual threads on the fly and letting them die is okay. This is actually what you should be doing. You can submit tasks in the form of runnable or callables to this object. These tasks will be executed in a virtual thread, and then you can analyze the result. And once you're done, this pool of thread is closed, and everything that was left over is actually cleaned up and garbaged for you. So nothing can escape.
Yeah. So technically, it's not a pool of thread because you don't want to reuse those objects. It's more something that will care of a list of virtual threads.
Plus, when you create it, there's no thread in it. It's empty. You create threads on demand. So the pattern of code is the following. So there was a first version of the Structured Task Scope API in which Structured Task Scope was actually a class and it was not final, and you could extend it. Now it is an interface that is sealed, so you cannot implement it yourself. Okay, you need to rely on the implementation that is given to you by the API and that you don't see, by the way. So you call open, which is the factory method, and this object implements autoclosable, meaning that you should be doing that in a try with resource statement. And we'll see what is happening when the close method is called, but basically all the resources that were resolved within that are cleaned up. In a first step, you need to fork your task. So this is the submission of your runnable or callable to this structured task scope object. In exchange, you get an object, which is a subtask, another interface given to you by the API. And you can see a subtask as some kind of future-like object because you have a get method on it. But it's not a future because it doesn't work exactly in the same way. And at some point, you need to call the join method of this scope object. And this is very important to call this join method because if you don't, you will get exceptions. If you call close without having called join, you will get an exception because you're not supposed to do that. And if you want to analyze your result before calling join, you also get an exception. So calling join is, important. It's a blocking call, but it's a virtual thread, so being blocking is okay. This is what you should be doing. And once you've done that, you can just call get. And if you call get, you're quite confident because you know that there is a result in your subtask object. If you're not confident in that, you can also, we'll see that later, but you can also check the state of this object and see if there is actually a result or an exception. But this is what you could be doing and then return page or do something with page. So that's the basic pattern of this structured task scope object, and we're going to see much more about it later. So close is called when you exit the try block. it tries to shut down all the threads and everything that was created within the scope object. And if your virtual thread, if the callable of your virtual thread is itself creating another structured task scope, then this structured task scope will also be closed when you close the mother structured task scope. Okay, and it can throw an exception if it will throw an exception if join was not called before you call the close. I already said that. The subtask object is this one. So it really looks like a future. You have a get method and an exception method that returns the throwable. The exception doesn't throw an exception. It gives you the exception that your callable actually threw. And it has this state object, and we're going to see the life cycle of this object. So which can have 3 states actually: success, failed, and unavailable. If the subtask object is still if the callable corresponding to the subtask object is still running. Okay, and we'll see more about that in a minute. What if a callable throws an exception? Well, you can have actually several behavior. By default, in this case, you will have a failed exception thrown by this join call that is wrapping the exception thrown by your callable. Okay.
Yeah.
So,
and because this is a modern code, this is a runtime exception.
Yeah. So you don't need to catch it.
If you don't.
What do you mean modern code? And what if a callable throws an exception? Because we talked to you about the stack traces that you get. Well, so if this readImage method throws its boom exception, as we saw earlier, you can catch the exception, the failed exception that will be thrown by the join call to preserve the thread you're in. And you need to analyze the image subtask object. Analyze, in a case it is in a failed state, and then get the exception and do something with it, like printing the stack trace, which is stupid, but why not? And the stack trace will be this one. So the stack trace, once again, takes you exactly, because it's based on virtual thread, where you submitted the code, where the lambda was, and it will take you to some services. So gone are the days where you have stack traces that you cannot use to debug your code. You'll actually be able to debug this properly directly by going directly where the exception was thrown in your code. You can configure this structured task scope object by passing, first you need to pass a joiner, and we're going to talk more about joiners in a minute. But you can also pass a lambda, which is a builder, that takes the configuration of this structured task scope, and you can specify the name. So with name specifies the name of this scope object that will appear in thread dumps if you're doing thread dumps. You can also specify the name of the threads by passing a thread factory. And you can also specify a timeout if you want to set a timeout on the global scope object that you have. This is how you can do it.
Yeah, I have call it the Ruby builder pattern because I have seen first in Ruby, but I don't know what is the name of. You want a builder, but you are not creating yourself the builder. The builder is given to you, and you have your this is box. The way you cannot use the builder outside of the open method. You can only use it to configure the whole thing. It's a really nice pattern. I really like it.
I do too.
And GetOpt on Ruby works that way.
And I think we can take a break here.
It seems.
Coffee break? Who doesn't like coffee? Okay. Oh, there are still several people that don't like. What about we start again in 25 minutes? Is it okay? Okay. So 3:10. We'll start again at 3:10. Thank you. And see you in 25 minutes.
Okay.
Welcome back.
We are back.
I hope the coffee was good. I hope you enjoyed it. Maybe you had something else. Just before we start again, you can actually rate the talk, especially if you want to put 5 stars. If you don't, you can just skip it. But yeah. No, I'm kidding. We always value feedback very much. So yes, if you have a few minutes to do that, definitely you should be doing it. Okay, so we just presented this structured task scope interface API, and we're going to deep dive a little more in this task scope, present you how you can actually define strategies for doing several things with them, and show you a demo.
So basically the demo is like a quiz, which is, did you understand all the slides we have before?
Of course not. Okay, so structured task scope, you open it, you fork, you call join, and then you do what you want with it. After that, if you don't call join, you will suffer the pain of having exceptions because you need to call join. But the fact is, and I don't know if you remember the slide with the configuration, but actually the first element in the configuration was a joiner, and you can pass a joiner to the opening of this structured task scope. And actually, maybe some of you remember the previous version of the API, but to create your own strategy of dealing with all the tasks that you launch in a structured task scope, you had to either rely on existing strategies or extend the structured task scope class. Now it's not the case anymore. Structured task scope is a sealed interface. You cannot extend it, but through this joiner object, you can actually define your own strategy on how you want the structured task scope to exactly work. So basically, you create this joiner, open your structured task scope, pass a joiner as an argument, and this joiner will act as a callback, global callback on the life cycle of the different tasks that you're going to submit to fork to this structured task scope. Okay. The join method can return a result, and you see that this joiner is the joiner of T and R. T is the type of the callable you can submit, so it could be void in the case you pass runables. And R is the element you want to return from your join. Sometimes it can be void, or the type can be void, so you are going to return null objects and do something else. But sometimes you can also produce a result, and in that case, your joiner can specify what you want to return, the object you want to return. So the joiner interface, the joiner is an interface. It's an old API in itself, and to define this strategy. And there are several things you want to define. How the result of a task that you submitted impact the behavior of the structured task scope. Should a task that is failing with an exception cancel the scope? Should a task that is a success cause the join method to return and the result to be produced? This kind of thing, you can all define it. And you can also decide to actually interrupt a scope while there are virtual threads that are running. So you can do two things. First, decide on the strategy to cancel a scope if you want, or let it run until all the tasks are done, and decide on how to create a result from this scope. Okay, and that's it. So this joiner interface has two groups of methods. The first group is actually two callbacks. The first one is onFork. It takes a subtask, and we're going to see how this onFork method is called by the API. And you also have an onComplete method. Both take the subtask object, so it's called when the subtask is built. And you have two other methods. One of them is result, and this method result will actually return an object that will be itself returned by the join call that you have in the structured task scope pattern. And in 26, this method does not exist in the 25 version, but in 26, you will have an onTimeout method that returns void, and that will be called if the scope object is timing out. Right? When you create your scope object, you can define a timeout, and this timeout is reached, actually it will interrupt all the threads, and then it will call this onTimeout callback from your joiner.
Yeah. So you can decide to close things.
Yeah. If do something. So if we take a closer look at how the joiner is working, it's working in this way. So you have your main thread that could be a virtual thread, by the way, okay, that is creating a structured task scope object. So the structured task scope object is created, and you start. Once you've done that, you start forking tasks. You have passed a joiner to this open method. It should be on the slide. It's not. That's a mistake. So you fork a first task in the second step once it has been opened, and then three things are happening. First, there is a subtask object that is created, and the state object of this object is unavailable because there's no result yet. Your callable has not even been launched in the virtual thread. Then, second, the call from your joiner.unfork is called with this subtask object. Okay, and then a virtual thread is created that is going to run either the runnable or the callable that you submitted to this STS object. Okay, so here you can see that this unfork method will take the subtask object that is in the state unavailable, and it will always be like that. All right, and second, it is called in the main thread that created your scope object. And this is very important to understand this threading stuff because it will not be the same with the onComplete. Unfork is called before the virtual thread is created, so it cannot be called in that virtual thread just because it doesn't exist yet. All right? So once this is done, you have forked your all element, you call join, and this is this red stuff that is there. You call join, and this join call is blocking. So you're waiting for your task to be executed by your virtual thread. And if you submitted several tasks, let's say 4 tasks, okay, these tasks are going to be executed in the virtual thread, and they are running currently. So all the state of the subtasks are still unavailable, and the unfork method have already been called because the virtual thread are now existing. All right? And then you call join at this point. This join call is blocking, so you're just waiting for the result, for the results of your tasks to arrive. And then at some point, one of the tasks will complete, either with a result or with an exception. The first thing that is done is that the subtask state is updated, so it will move from unavailable to either success or failed, depending on what is produced, a result or an exception. And then the onComplete with the subtask as a parameter is called. All right? So this onComplete is called in the virtual thread that executed your callable or your runnable. So the unfork is called in the main thread. The onComplete method, one per task, is called in each virtual thread that actually executed your task. So you may have concurrency issues if you're not cautious on this one. Then after a while, so suppose that this first task generated an exception, so the subtask state is now failed for this one. Then after a while, another task complete. So same, onComplete is called in this virtual thread. No, sorry. The state of the subtask is updated. Then onComplete is called within this virtual thread, by this virtual thread. Okay? And the state could be success. Who knows? Yeah. Whatever. So you have a result. Great. And then same for the next task, and then the same for the next task. All right? When all these tasks are done, either with a success or a failure, then your join call will return. All right? And then you will be able to act, get this subtask object, because this subtask object, remember, are returned by your fork call. So you have access to this subtask object within the code that is executing your subtask scope. Then you can call either get or exception on this subtask object after the join returned. If you try to do that before, then you will get an exception. You can't. Okay? And then you can get all the results of your subtask object and produce a global result for this scope and return this result and carry on. But sometimes, onFork and onComplete, they all return a Boolean. And this Boolean will tell the structured task scope if it is allowed to continue running or not. Okay? If this Boolean is false, the structured task scope can carry on. If it is true, then it will stop, try to stop, and interrupt the thread. So suppose that for the first one, return false. For the second one, onComplete decides to return true. Then it means that this structured task scope is done. It should be interrupted. Well, the thread should be interrupted, and the structured task scope should be closed after that. So what is happening in that case? First, all the threads are interrupted. Interrupted meaning that they won't stop right now. It will take a little amount of time, right? And the join returns. So now, if you analyze the subtasks within your structured task scope code, it means that some of the state will be unavailable, some of them will be failed, and some of them will be success. Note that the thread that is interrupted can still generate a result, because if you don't interrupt it fast enough, then it can still produce a result. So this subtask could be either failed or success, but not available. And you can observe that, actually. It's quite easy to observe. Okay, so it's not because the thread has been interrupted that the subtask will be in a state unavailable all the time. And then, because you call join return, so you can analyze the result of the subtasks, and you can, at some point, your structured task scope, well, you can produce a result, and then your scope will carry on. Okay? But it may happen that the interruption will not work, and that you have a loose thread that will continue running. Okay? And this is embarrassing because it means that the close method will try to interrupt the thread itself, but if it doesn't manage to interrupt this thread may be running forever, and your structured task scope will also be running forever. So you need to be careful with that.
But it's better, in fact.
It's better now because you know. It's a bug, because now you know that you have a loose thread. Before you didn't know, and now you know that. And you need to do something about it, like stop calling non-blocking code in a virtual thread, which is the principle we talked about earlier.
Stop catching interrupt exception.
You didn't necessarily catch the interrupted exception, but yeah.
You should not.
Probably you did. So this is this kind of, way of the joiner is working. The main thing you need to keep in mind is that unfork is called in a main thread, and onComplete is called in all the virtual threads. So if you're doing some kind of mutation in onComplete, you need to keep in mind that first it will be subject to race conditions, so you need to protect yourself against that. And second, it will be more expensive than doing it in onFork, because you will have synchronization and visibility to fix. You need to do that. So this is how this joiner is working. Now, that being said, the joiner defines when the whole computation is complete. Okay, for instance, if you're querying a DNS, you're only interested in the first result because all the other results will be equivalent. So as soon as you have a first result that is, that is a success, then what you want is get this result and cancel the rest. Okay, so having exceptions may not be an issue. Maybe it is, maybe it is not. It really depends on your use case, on your application use case. But the joiner interface is versatile enough so that you can really define the strategy you want to implement. Do you want to talk about the standard joiners?
Yes. So by default, you have several joiners. They are not in the class called joiners because we are now modern. We can have static methods inside an interface. So they are directly in the joiner interface. So the first one is all successful result. Oops, there is a bug in the slide. The name of the method is all successful result or throw. So it returns a joiner, and basically the result of the method join will return a stream of subtask of T. This is what you see in the declaration, and it works that way. If one of the tasks throw an exception, then all the other tasks are cancelled. Yes? So the result is a stream. There is no real reason why the result is a stream and not a list. But Anyway, this is how it works.
The stream is created once the join has been called, right?
The stream is created once the join is called. So the stream is created by the main thread, not by another thread. So we have any successful result or throw. This one will return the result of the first task that succeed. And it will throw an exception if all tasks fail. You don't know if the resulting task is the first one or not. You just know that one will succeed. Not necessarily the first one. We have one which is a little more involved. It's called until, and it takes a predicate on the subtask. So you can say all until one task succeed, or on until one task fail, or things like that directly. And it returns again a stream of subtask for the same reason. You should not do any side effect inside predicate, because the predicate will be called by each virtual thread, which is dangerous.
The predicate is called in incomplete. So yeah.
Yes, the predicate will be called in incomplete. So it's quite dangerous if you do a predicate that changes the value of some field or things like this. It will not work as intended. This is clearly written in the spec. I'm just quoting the spec. You have await all successful or throw. So it's like all successful or slow, but it will not return any result. It will always return null. The result value, the result method will always return null. So it's up to you to manage all the subtasks. And we have await all. Here you are on your own, which is basically even if one task fail or if one task succeed, the task scope will do nothing. So basically, if you are using await all, after the join, you will have to analyze all the subtasks to know what to do. So it's just something that will run everything until they all complete. So we tried to put them in a kind of way to see the things. So with a joiner, you can do two things. The first one is the condition on the wait. Do you wait for all the results? Do you wait on a predicate? Or do you wait on the first result? That's the first axis. The second one is what you return. Do you return always null, one result, or a stream of all results? And basically, there is a third axis. I don't know if you see it, but you have the or throw axis. Some methods are named or throw. For all of them, it means that if one task fails, then the whole scope fails.
And I think we're switching machines.
Yes. Demo, yeah. So for a demo, there is one thing which is important is that...
But by the way, the demo that you're going to see is on... is it mine? Yeah, it's my GitHub account. So if you
yes,
want to see it...
It's called 2025 Devox.
Loom. I think there's Loom in it.
There's Loom in it. It seems there is Loom in the title somewhere here. So we should go to the slides.
Yes, but you don't have the slides anymore.
Oh, yeah. Sorry. So I will explain. So it's a pseudo. Let's take a real example. So you are a travel agency and you are depending on two different services. One gives you the weather, but you have not only one services that give you the weather, you have several services that can give you the weather. Here we have a server. You write the code using Elidon. I don't know exactly why.
I don't know neither. Because Elidon is built on virtual threads, and we're talking about virtual.
Yeah. True. It means that all for the server part, all those thingy. So here you have something like, if I see /cities, I will execute this inside a virtual thread, which is kind of nice. So let's start that server. So the server starts, yes. And there is another.
You can show it if you want. If you click on this, you have
on this what?
On this link, the HTTP link that you have in the console.
Oh yeah. Oh yes.
You have a beautiful interface.
So yes, you can see the result of you have cities and you have the weather of the city. Like you can get the weather of Atlanta.
It's random, so if you click again, you will have a different result, I guess.
No, it's always sunny. No, it's not in Atlanta. No, it's always sunny and hot in Atlanta. So this is the first services. We have another services that give you flight. So this is a company server that give you flight, and I suppose that if I click on that things, I will see some flight. So you can choose the city of departure, destination, and it will give you either a direct flight. Is it working?
It is.
It is?
Or if you want to go, yeah.
Austin, Atlanta to Austin. And you have several companies that try to.
You can try the other. You
serve.
Have at least one
Nope.
That is working.
Nope.
Oh my god.
Nope. Nope. Don't use random data. Let's go to Seattle. Atlanta to Seattle. And nope. Nope. Anyway, when there is a saying I should not do any demo, but anyway. So I have both my server that I've started, and I will do 3 different demo. So the first one is to ask for the weather to the first server. So we are interested by that code. So I have a list of agency, and for each agency, I want to ask what is the weather for this city. So obviously I want to create a weather query on each city. So you can see the weather query is just something that will use HTTP client and post the value, and if the value is 200, then I know that the JSON is a weather, or throw an exception, and I will explain why throwing an exception. So the structured task scope, let's call it STS. The STS is configured with a joiner that will stop once there is at least one result. There is something quite interesting, which is you can take a look to the code of this default joiner, and you can see that, so you have some funny thingy, but this is the field which is important. In terms of implementation, I have a subtask, and if one task complete in onComplete, I will try to store the subtask. And obviously, I only do it if the subtask, the field of the subtask is null, and I will update if, so basically, if one is failed and the other is success, the comparator will be higher, so I will try to update again. And here, I will say if the STS should stop or not. If it's success, if the state is success, then I'm okay. The main issue is that onComplete is called by different virtual thread, so you have to use volatile, and here, because we want to update the task here, we are using a concurrent set for doing this, because we don't want to pay too much for that. So basically, we have several threads that will race to update this field. And if one task failed, it will put itself as a subtask. And if one succeed, it will put itself replacing the one that failed. That works that way. And you can see the result, basically reading the field. If there is no subtask, it means that all have all tasks never complete. Otherwise, if it's success, it will return the value of the subtask. Otherwise, it will throw the exception. So this is basically the way it works. That's why here I need to throw an exception, because either it succeed or it fail, and I need to know if it succeed or fail. So there is something which is we have no way to say even if it succeed, if the value is not the right one. I would want to have something to parameterize the success or not, but I'm not able to do that with that joiner. So it works that way. I just fork all the things. I get the result here. If all the tasks are failed, then I catch the failed exception and just return optional empty here. So this is the first task scope. Is it okay for everybody? Yes?
Did you use this unnamed variable?
Oh, yes, we are in Java 25. I can use underscore and it works. And so we can go to the second example. In the second example, here I want to query the different flight. So I have another structured task scope. I will open it with await all. So await all means all thread will run and there will be no cancellation at all. They have to all run. So here I just submit, I will fork for each company, I will fork and ask for the price and get the price, join, this will wait all the task to complete, and then I need to analyze all the subtasks to know if it failed or not. So I get all the subtasks. So here, await all return null. So I cannot use the result of join. To get the result, that's why I have a stream here, is that I will take all the result of all the fork, put them in a list, so I can analyze them here. Which is a kind of sad that I have to do that. Anyway, so I can switch and know if the subtask succeed or not. So if it's a success, I will keep them. Technically, what I get is as optional, so I need to flat map them if the optional is empty. And obviously, what I want is the cheapest flight. So the great thing here is that I have a complete separation about what is the semantics for the STS, when to stop it, and I'm able to write my business code directly on the result, the way I want. So we can run it. I hope it will work. So yes, if I go, so it seems that the company Norwegian Parrot has the best flight. It's a multi-leg flight between Phoenix to Philadelphia via Boston. Anyway, and I have the price here. And then I have another things, which is now I want to query a travel. So what is a travel? A travel is something that asks for a flight and asks for the weather on the destination of the city. Obviously, the weather is less important than the flight. So if the flight is answering, first I will not wait for the weather. I can implement this kind of things. And the way I use it is by calling the other to query I have used, which means that this structured task scope is forking something that itself is a structured task scope, which means that I'm starting to use structured task scope inside structured task scope. So in this case, basically I want to wait until I have the result of the flight. So I will fork the weather, the weather task, I will fork the flight task, and I'm using all until. And here I check if it's a success, and if it's the company flight, I will return true, which means that onComplete will return true, which means that the structured task scope is completed. So it will stop at that point if this query, the weather forecast query, has not finished, it will cancel it. So I'm able to say, I want a flight, and if there is a weather, that's great, but if there isn't, I don't care. So obviously, when I join here, I need to check the state of the weather. For that, I'll use the weather task here. And here you can see that because I'm using the result of fork, I can have the exact result in terms of typing. I know that this is a subtask of optional weather or a subtask of optional company flight, which means that when I get the subtask here, I can ask for the result of a precise subtask, which means that they are typed correctly, which means that when I ask here for if it succeed, give me the value will be an optional of weather. So obviously, if the optional if it doesn't succeed, I will return empty, and here I will send the weather as an optional value, which is if I run here, I have an optional weather, and if I run it several times, I hope that at some point, no, I have another weather. So there is a way to do it.
Yeah.
So in this one,
you can actually do that in the weather.
I will just thread.slip. Wait. Okay. Oh yeah. Okay. For once it works, but let's say it's a demo. We don't care. And here,
never tell anyone you saw Remi doing.
Yeah. It's really bad, but.
Didn't you say you should know that you should never do that?
You should never do that.
This guy has students.
Technically, I propagate the exception. It's not that bad. I didn't log it.
I'm not sure you
because if I
convince these people, right?
No, I will not. But technically, I didn't log it and do nothing. At least I propagate it. So in that case, I can see that the weather is empty because in my structured task scope, I will not wait for the result. So it means that if I have several tasks that works the same way, I can use the result of join and getting the list of the task. But if I have here two different tasks that works very differently, I can use them as a kind of snowflake. If one is a snowflake and doesn't have exactly the same result as the other one, and I will just name them, get their subtask, and use them differently to aggregate the value I want, basically, which is kind of nice. Another thing I want to show you is how to do proper debugging, which is Usually, when you have a debug mode, you have something which is either you enable the debug mode and you have the debug mode for everywhere in the program, or you have the debugging mode for nowhere in the program. You can do better. You can do things like this, which is, for this query, I don't want the debug, but for this query, I want the debug. How to do this? Let's take a look. We have a scope value here, which is a scope value of Boolean. And so basically, when I read it, I will take a look if the value is bound or not. If the value is bound, then I will execute this supplier and print the value. If the debug is not set, if the scope value is not set, then I will not print the debug message. And here I have a debug call that takes basically a callable. It's a callable that precisely tracks the exception. So it will propagate the right exception through it. And I will set the value of my scope value and then call the exception and call the function. If I run it, you can see that for the first call, there is no debug. But for the second call, you have the debug that are enabled for it, which is really nice. I hope all logger will work that way now. It would be cool. If you think about it, when I call debug call, it will call the travel query, and the travel query has an STS that will call the fork here, and inside the fork here, you call the weather query, and only the weather query does the log debug, which means that my scope value that I have set in the first in the method that will call the first STS will propagate the scope value to the first STS and then propagate the value to the two other STS automatically, which is a really, really nice feature. It works. So that's all for the demo. We can
switch back to the
slides.
Oh, marvelous. Okay, so this was for the demo. I would like to focus a little on the joiner, because the joiner can actually be used to cancel the scope, but it can also be used to produce a result. And you use the min joiner, and here we have a max joiner, which is kind of the same. Just switch the min to the max, and that would be it. And you see that in that case, this max joiner is actually working on the unfork callback method by adding all the subtasks to this array list which is declared in this Mac joiner, and return false because if you return true, remember that if you return true, you are actually asking to close the STS. So it will close the join method to return and the STS to be closed in the end. And because this result, there's this other method called result, and the result of this result method is actually called by the join method to produce its own result. So when you pass a joiner to the opening of a structured task scope, you can actually also produce your result within this joiner and directly return it with the join call. So it may lead to code that is a little more complex, but it also allows you to really unit test your business code, and this is business code, in isolation of the structured task group itself, which is probably...
Yeah. Technically, there is just only one problem. If you take a look to the doc, the Java doc of joiner, there is a line saying, please do not implement your business code inside the joiner. Because basically you can implement it outside of the joiner. That's why all the methods return a stream.
Yeah.
Because you can, basically the part that will take the stream and filter should be inside the joiner, but the max part, the one that do the max, should be outside of the joiner. So you can reuse your joiner if you want to do a minimum or things like this.
Yeah, absolutely. So if you do it in that way, the result method is also called in a main thread that creates your structured task scope, and by the way, also creates the joiner. So that's the first solution. And you see that here you don't need to think about synchronization or volatility or any kind of thing, because all the method, if I go back one slide, this unfork method and this result method and the creation of the joiner are actually all called from the same thread, which is the main thread that created the structured task scope. Now, if you try to do the same kind of thing from the onComplete method, now you need to be careful because onComplete is going to be called on each virtual thread. If you have 50 different tasks, different callables that are going to be called, that are managed by your structured task scope, onComplete will be called 50 times, one per task, and each onComplete will be called in a virtual thread that actually executed your callable or your runnable. So now you have two possible race conditions. The first one is that you can't add element to a release because the release is absolutely not thread safe. So if you do that, you will lose elements. You can actually even have null pointer exceptions on the add method.
You can have, but because one thread can see.
You're really unlucky.
At least you can see you will have array out of bound exception, because you can have one thread that resize and the other using the old backing up array. So
really very bad things happen.
Just awful.
And I would say that's the easy race condition to see, but actually you have another one which is also on the read of the subtasks field, which is actually created by the thread that is creating the structured task scope and read by the virtual thread. So here it's final, so it's okay because final has this semantic of making your fields visible from other threads. But if you forget to make it final, then you also have a race condition and a reading of the subtask reference.
You will have a null pointer when you try to call add.
Which is even better.
Yes, and only on Mac.
Only on Mac? Oh.
No, technically, if you are on Intel, you have a total store order that it will work.
It's not the case on Mac. It's not a Mac.
No, it's because it's an ARM. It's not the problem of a Mac. It's because it's an ARM.
Okay, so you need to have a concurrent aware collection if you do that. And by the way, concurrent link queue is not a list, so now you have a collection. If you're just doing a stream on it, it's really not bad.
But yeah.
But you need to be aware of that. And you need also to be aware that you need to have a field that is either final or volatile. And this is what you showed on the joiner. And obviously, this solution should absolutely be avoided because it will be much more inefficient than the other one. because of all this synchronization.
If you think it means that here you are adding, every time you do an add, you have to do a write on a field which is shared by several virtual threads. So you don't want to do it that way. Basically, the API should be used in a way which is you try to be as lightweight as possible inside the complete, and then you do a post treatment at the end and filter the result you want.
Yeah.
Because in that case, you are in the main thread when you ask for the result.
Absolutely. And I think this is what we wanted to tell you about virtual threads today. Where are we currently? So virtual threads have been made final in 21, so it is still final in 25.
Yes.
When it's final, it's final. But it was improved in 25.
Yes.
So you should. That's definitely a good reason for moving. If you
are using virtual thread, please use 25.
If you took 21 to use virtual thread, then you should take 25 as soon as possible, as soon as you can. By the way, you could also have taken 24 because 24. It's not because it's not an LTS that it's not a version that is robust and the same level of quality as the LTS versions.
Yeah, but it's already 6 months after the release of 24.
No, I said you could have taken 24.
Oh, okay. Sorry. Yes.
It's too late to take 24.
Yes.
Scope values are final in 25.
Yeah.
Definitely. So yeah.
So you can now debug only one call.
Yeah. Structured concurrency will be in preview in 26. We already know that because we have the JEP with the 6th preview.
And please test.
Yeah.
Try to use it and report.
And the difference we saw on the API is that you have this on timeout method on the joiner interface that is in 26 and that is not in 25.
Yeah.
Okay. You can also download a lab that we did this morning with the. It's actually the demo you showed.
Yeah.
With more things and it's
more or less. Yes.
More or less.
More or less.
Oh, you mean the demo you showed?
Yes.
Yes, it's more or less that, but there are more things in it. So if you want to do that, and by the way, if you couldn't attend the lab this morning, you'll be able to attend it tomorrow afternoon because we are making it a second time because there were like 200 people registered to the lab and only 50 seats in the room. So we're doing it again tomorrow afternoon. So you need to check the agenda of that. And I think we have plenty of time for questions.
Yes.
Which is nice. Any question? Anyone? Yeah, there's a question just over there. You need to shout so loud, please. Okay, perfect. Thank you. Yeah? So the question is there a reason why the joiner method doesn't have is successful or is, I guess, is unavailable or is a failing method?
So yes, because the idea is to do a switch on the state, so you will not miss a state, basically.
Is there
at least this is the reason Alan Bateman
is saying.
Give to me.
So you won't have a successful method in case this is what you.
You want a method that return a boolean? Yes. Yes.
Yeah.
Yes.
So the objection is that it would be nice to call a method reference.
Yes.
That would return true or false instead of and filtering directly instead of checking with a switch, which kind of makes sense.
I want.
You want to show something?
I just wonder if the method doesn't exist yet, just to be sure. Is
there another question in the meantime? Yeah, question. So the question is for the on timeout, why isn't there a subtask parameter? Subtask is an object you get when you fork. So you're not responsible for the creation of this object. So maybe you could fork with the timeout. But actually, the choice has been made to create the timeout directly on the global scope itself through the configuration. And this is the choice which has been made. So you cannot time out. I'm not sure it would make sense to time out each task individually with different values, because if a task fails with the timeout, then what is going to happen for the others?
Yep.
You probably want to common timeout for all your tasks.
You can still do it because you can create one structured task scope per task.
Yeah.
But
yeah, exactly. Do you have the?
Yeah. There is no method.
Okay, there's no method. As expected. Yeah. Other question? No. So the question is about canceling all the tasks. When you decide to cancel, actually what you decide to cancel is the scope itself. And by sending some kind of cancel signal to the scope will interrupt the threads that are running, using the classical interrupt mechanism, by the way. So that's one more reason why you should not have any in-memory computations that can just run forever because it's buggy. Because if you don't manage this interrupted state properly, like it was in Java 1.0 or 1.1, then your scope cannot be closed and the close method will never return, basically. Oh, you mean a default behavior if a task fails? Then this is something you can that's the job of the joiner, actually. So you can totally implement a joiner. Is it a standard joiner? A joiner that would cancel the scope on the first exception that is thrown?
Yeah. All the joiners that have a name that finish with or throw works that way.
Okay, so you already have that, actually. But if you want to do something like you would accept, suppose you're forking a certain amount of tasks, and you just accept like 10 failing tasks, and you want to cancel after 10. So you can increment a counter within your joiner, and then totally do that. Yeah, so the one failure that should close your scope is actually one of the standard joiners that is available, given by the API to you. But if you want to do something more, fine, you have total control on that, actually. Yeah. Any other question? Yeah. That's a question for you, Remi.
So in the demo, I didn't.
We need to repeat.
Oh, sorry.
So the question was about the proper
way to deal with interrupted
exception.
So interrupted exception is problematic for several reasons. But what you should do usually is just to try to throw it. What I've shown in the demo is you can catch it and throw another exception for it. It will work because at the end, it ends the whole virtual thread, which is what you want. Basically, if the virtual thread is interrupted, you want to end it. So it works as well. You can use thread.current thread.interrupt to interrupt yourself. The main issue is that you will continue to execute the code. Yeah, but if I throw the exception, I know that I will not run any other code. If I interrupt myself, I will run other code. And if this code is slow, basically I'm not interrupting anything. I fail the contract of I should interrupt the whole things.
What I'm saying is just you should have done two things. Set the interrupt flag and then immediately throw the exception.
No, in that case, throwing the exception is enough. No, it's basically if you get an interrupt signal, you want to stop everything you are doing. That's what interrupt means. The whole things to re-interrupt yourself is more something of the past. Usually, it's better to throw an exception that you know nobody will use. And usually, you don't throw an exception, but you throw an error. In that case, you know that no one is stupid enough to write a catch error, right?
An out-of-memory error, maybe? Are there any other questions? Yeah. Yeah. So the question is on the return value boolean of unfork and onComplete that is used to cancel the structured task scope. And the question is, wouldn't it be nicer to return something that would have a business meaning, like stop or cancel or stop doing that? Or why would you continue doing that? Maybe that's a question for the mailing list, by the way.
Yeah, but I think the idea was not a lot of people will write joiners. You will use the one that I provided by default. And by the way, if you think that there is a missing joiner, it's something you should send to the mailing list. Because at some point there will no, it's quite easy currently to add a new joiner, I think, because it's only
a preview feature.
It's a preview feature. It will be harder to get a joiner that you want in it later.
So to do that, you need to go to the openjdk.org website and visit the Loom page, and you have the different Loom mailing lists in which you can post your use case. Any other question? Yeah, over there. So for virtual threads, yes, we do. Scope values were made final just a few weeks ago, so it's probably a little early. Structured concurrency is not final yet, so having feedback on what frameworks are doing with it, it's probably a little early.
So I have seen a framework that was using that had a flag that was using either ThreadLocal or scope value, depending, basically sniffing the version of Java you are using and using one or the other. And I think more and more frameworks will work that way.
So one important point that we need to mention is that virtual threads are compatible with ThreadLocal variables. So if you keep using your ThreadLocal variable system with virtual threads, it should work out of the box with no problem. Scope values are an alternative solution that works better and gives you, hopefully, could give you better performance because it can be optimized at the JVM level, while ThreadLocal can't be because of things that we said during the presentation. But so you can imagine a path where you don't need to move all your ThreadLocal variables to scope values at first, because even if you're using and benefiting from the use of virtual threads in your application, then your ThreadLocal variable system should still be working.
So I know that at some point, there was an experiment to try to use ThreadLocal with basically a scope value inside, and saying if you use it correctly, it will work. But sadly, you have so many ways to use a ThreadLocal not correctly that there is no direct replacement. It's a new API. Yeah, but if it's hidden in a way, it's not your problem.
Question?
Just shortly to this question, I remember in the beginning when the thread local was introduced, some frameworks has a problem that they say abuse little bit local thread local like a cache to fulfill some data inside that the thread will be pulled next time and has been pre-initialized structure. And this doesn't work anymore with virtual threads because virtual threads kind of built and not exist anymore for the next one.
So yes. So your question is so it's more state as a fact that yes, if you are using virtual thread and thread local, at least you have less leak of data structure that stay in thread local.
Yeah.
Because you are killing actually the virtual thread.
Use this fact to kind of cache the reloaded data.
Yes.
It's of course broken.
Yes. So yeah, in a perfect world, everyone will use at least call remove on the
When you're
on
done.
the thread local but yes, the world is
I'm
more.
not so
is
sure
more
that
messy.
leaking data is actually a desirable effect of thread local variables, to be honest. Leaking like security secrets or this kind of thing, I'm not sure that this is something that you should look for in your application. And that's one of the issues, because thread local was designed in 1998, that was Java 2, and the executor service where you actually create your threads up front when your application starts and never kill them was introduced in Java 4, that is, Java 5, 2004, that is 6 years later. Right? 6 years is a lot when you think about it. So people were using threads and creating them and would let them die because everything was so slow at the time. People thought it was fast, but now we know that it was slow. That it was okay to do that. But then you have this system where your thread never dies, and then if you don't never call remove on your thread local variable, then you have leaking. That was not the case before because the thread was dying anyway. So nothing could leak at the time. But now in 2004, things start to leak, and they are still leaking today. So that was a very long leak, and it's a big issue, I think.
There's another question.
Yeah. So the question is, what would you recommend for async programming in 25, since the STS API is still in preview?
That's a really good question.
I would certainly not. That's a trick. It's a trick question, actually.
So I think you should answer.
Sorry, no, the answer is clearly use what you want to use. No, there's no good answer to that, because it depends on your application, it depends on your use cases, it depends on your team and what the people you work with are actually used to be working with. By all means, do that. That's your choice.
Yes.
So
Every time you bring out a new JDK, I have to go through.
you can use preview features in your production environment if you want. That is really your choice. But the price to pay is that you will need to update for every version, that's for sure. And the price to pay is also that you may encounter bugs that have not been fixed yet. And yeah.
Yeah. So since 19, at least now you have a method close on executor or executor service, which means that you can have you can use an executor not as a pool with a really long lifetime, but you can use it with a shorter lifetime. But you will pay the cost of creating your thread upfront.
But what you could do is actually create a first executor service that will asynchronously create executor services on demand so that the creation of this thread doesn't block your thread.
Yeah.
And make your code totally unreadable in the process, even more unreadable than what it is. This is a solution, yeah. People write reactive programming. They used to write in unreadable code, so yeah. It's just another level, another challenge.
But you don't have to use a structured task for task scope now. It's still in preview. It's fine to use whatever Spring or Quarkus give you, because I know Spring more, but anyway, it was retrofitted to use virtual thread. So at least...
There is an executor service, which is final, by the way. It's not a preview feature anymore. We showed it in the first part of the presentation, which actually creates one virtual thread every time you submit something to it. And this is auto-closable. So actually, you can use it in a try with resources statement, fork your stuff, and kind of fake the use of a structured task scope in preparation of the final version of the STS API. Yeah. That could be a first part, because once you have that, you have your futures, and then you can get on your futures, and you can kind of do the same kind of thing.
But
that could be a poor man's version of the STS.
But you will still have the problem of if you use it in a try.
I'm talking using it in a try with resources.
If you use it in a try with resources, I think you are. It's quite nice.
Yeah. By the way, if you play with var, if you put your futures in vars, then you may avoid having to change this code once the future becomes a subtask. I wouldn't rely on that too much, but
yes.
Yeah, you don't have joiners in the executor service, that's for sure. Yeah. Yes, question? So you can actually, so the question is about scope values, and I'm going to give you the answer. When you bind a value to your scope value and call a method, if this method needs to rebind this another value to this scope value while calling another method or another structured task scope, why not? Then you can do that, yes. But then it will hide the previous binding to the next call. So it works like a stack, and indeed it is stored in a stack, actually. So the answer is yes and yes. Any other questions? Maybe we have time for a few more questions. Yeah?
Yeah.
Sorry. Yeah. So that's a very good question, by the way. So the question is how the binding of scope values are transmitted to new threads. So you create a binding, you bind your scope value to a value, and you call a method, could be a runnable or a callable, it's basically a method. And if this method creates structured task scope because it's an auto-closable object, and its life cycle is actually bound to this method, or should be bound to this method, or let me say it in another way, you can bind this lifespan to the scope of this method, then the binding of your scope values will be seen in the virtual thread created within this STS. But if your method creates threads using new threads or the factory method you have on the thread class, whether these threads are native platform threads or virtual threads, then the binding will not be transmitted to this thread exactly for the reason you gave, which is that this thread can escape the scope of this method call, and you have no control of that. So in that case, if you create an executor service and you submit tasks to this executor service from within this method, then the binding of the scope value that was defined for this method call will not be transmitted, will not be seen by these other threads. And for stack reasons, by the way, because the stack will not be the same.
So it only works if you fork the virtual thread using the fork method of STS.
Yeah.
No, it
doesn't.
will not work. So basically, the scope value has to be created when you open the STS.
If you create the scope value within the STS, it will only be seen in a method called, because you need to pass a method called for the binding to be transmitted to. Okay, so it will be seen only within the scope of this method call. Yeah. I think we have the time for one last question, maybe. And the last question was actually the previous one, because we don't have any more. Okay, please. So the propagation of scope values from one thread to the other is automatic as long as it is in an STS and that you fork a task to the thread within this STS. You don't have to do anything. You don't have to do anything with that. Yeah. And if you rebind it and call it again, yes, it will also be transmitted. But this time it's not automatic. You are doing it manually.
Yes. And you have to see the scope value at that point.
Yeah. You want me to repeat that question for YouTube? It was a question about my retirement. Well, thank you. And I think we're out of time. Oh no, we have 20 seconds left actually.
So thank you.
So thank you for your attention. Have a great rest of the conference. And that's it.
Yeah.
Thank you so much.